Make sure to record. All right. So as I said on Friday, there was no reading guide as we're doing a little catch up. There we go. So the topic we will be talking about today is we're going to look at how proteins fold, right? So let me just get this out of the way. There we go. All right. So let's just start with the image on the right here. What we're looking at here on the right is called a folding funnel. And it's a way to visualize how proteins fold, right? And so in reality, this funnel is 3D, but what we're doing is we cut like the funnel in half so we can look at it. And the way to really look at this type of plot is that at the top up here, there's a lot of possibilities. So entropy is very high. Your protein can be in a lot of possibilities, but it's very high energy at the top of the funnel because it's not folded properly, right? So it's very positive energy at the top of the funnel, which is not good. Generally, you want negative energy. Negative energy is good when we talk about Gibbs free energy. Positive energy is generally bad. And so what happens is that as a protein folds, right, entropy will decrease, but energy is also decreasing. So that's good. And there's different folding funnels out there. This is just one type of folding funnel that says, like, depending on where you start folding, you can think of the top of the funnel as a bunch of different conformations of your protein when it's unfolded. But whenever your protein starts to fold, it will come to different pathways, different obstacles until you reach the bottom of the funnel in your native structure, or it means you're fully folded. Now, when we talk about folding proteins, it can take seconds for proteins to fold. That's actually quite a long time in talking about cells. So it takes a couple of seconds for your proteins to fold. If it's a small protein, you only need microseconds. So they fold much faster. And there's a lot of debate about how proteins actually fold. A lot of people have different theories. And generally what happens is that there's some kind of directed folding pathway. And so what happens is that we start with our protein, and it's folding as it's coming off the ribosome too. So this picture is a little bit deceiving in that it shows like your protein fully off of the ribosome. Your protein will start to fold while it's coming off the ribosome. And what will happen is that your secondary structures will form first. You'll form your alpha sheets, your alpha helixes in your beta sheets. And during that, you'll have your hydrophobic collapse, where all your hydrophobic amino acids will be pushed towards the center. And you're going to form your what's called a molten globule. That is, your protein will have like a hydrophobic core. Your protein will have alpha helixes and beta sheets, but you don't have your overall 3D structure yet. So after your hydrophobic collapse, generally what happens is that your subdomains will form. So your protein will start forming the subdomains it needs to form. And then you'll have some fine-tuned rearrangement after your subdomains form. Your side chains will slightly move. Any water that was trapped on the inside of your protein when your protein folded will be expelled by this slight movement of side chains. And in general, how protein folding works is that small areas of your protein will form first. So like I was saying, your alpha helixes, your beta sheets in your domain. And then once these small elements are formed, then the larger and larger elements are formed, right? Until you have a fully folded protein. So that's the general pathway for folding proteins. Secondary structure, hydrophobic collapse, domains, side chain rearrangement, and then you're done. So just to connect this idea of folding proteins with our discussion of free energy, if we're thinking about folding a protein, what are the signs of delta G, delta H, and delta S? Who can remember what those terms are all the way back from chapter 1 and how that relates to how a protein folds? Any ideas? Well, delta G, delta H, and delta S relate to a protein folding. Delta S is entropy, delta G is free energy, and delta H is enthalpy. So delta S is less entropy, so more stability. I don't know if I would say entropy means stability. Entropy is just different conformations. Just because you have a lot of different conformations doesn't, well, I just wouldn't use the word stable when it comes to entropy. Depends on what you mean by stable. So we have negative delta G, delta S positive. I don't know about that. Delta H is negative. I agree with that. Well, there is only one native structure, so your entropy is very, very low because you only have one possibility. Yeah, entropy is just how many different conformations can I be in? When you're not folded, there's a lot of not folded conformations. When you're folded, there's only one conformation. So delta S is negative, right? So it should be negative, 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 right? So let's talk about this. Why is delta G negative? Well, that means spontaneous, right? So when a protein is folding, it is spontaneous. Generally, for most proteins, we don't have to put energy in to fold it. It will fold by itself. So delta G is negative. Delta S, well, we're going from a lot of conformations to one conformation. So entropy, the number of possibilities is decreasing, right? The number of possibilities. Right. Delta H is actually kind of hard to talk about, and delta H is actually a big discussion in the world of biophysics about like what actually is contributing to this favorable free energy. But basically, delta H, you're making connections like how do I want to explain this? When you're pushing the hydrophobic groups towards the center, water enjoys that because water can hydrogen bond. So when delta H is negative, that means you're releasing energy into the world, which means you're making bonds. So making bonds, delta H equals negative. And again, there's a lot of debate what is contributing to that. But just know when you're folding a protein, you're making favorable interactions. Favorable interactions mean you're releasing heat. If you're releasing heat, delta H is negative. Questions about that idea? Delta G negative is spontaneous, fold by itself. Delta H negative, make bond. Delta S negative, number of possibilities decreasing. Basically, that's the answer, right? And so delta G being negative, it's barely negative too. Proteins are barely stable. We're talking like 10 kilojoules, and I know that number really doesn't mean much. But to put it in perspective, like one ATP, taking one phosphate off an ATP, that's you like ATP going to ADP. That's like 37 kilojoules per mole. A protein is favorable maybe by 10 kilojoules. So like just using 1/3 of a power of ATP, one molecule of ATP, you can unfold a protein. So proteins are barely stable, right? That's why when we talked about breaking open the cell, we have to be very careful about our conditions, because if it gets a little hot or the pH gets a little off balance, your protein will unfold super easily. So inside your cell, most proteins are barely stable when they're folded. So our next part is, I didn't talk about this, but there's little hills here in our folding funnel. What do those little hills mean? Can anyone hazard a guess what these little hills are? Why does my folding funnel have these little hills? Anyone have any guesses? Bonds forming? No, bond forming is good. Bond forming is negative energy. We want bonds to form. Unfavorable conformations. Yes, that is more or less correct. The word is would be intermediate states. It's the way to explain it. And let me get rid of some of my drawings here. So let's imagine you started right here as a protein. Energy minima, that's what I'm going to get into, like the exact vocab, right? Let's say you started here as a protein. Your goal is to reach the very bottom of this funnel. And so you're folding, you're folding, you're folding, and you come to right here. This is called a local energy minima. So let me explain those words or what that means. So as a protein, you're in a intermediate conformation. However, you are not in the correct conformation. But to get in the correct conformation, you have to break bonds. So basically, no matter what path you go to get out of this local energy minimum, you have to spend energy to get out of it. That's what that hill's saying. It's saying, if I want to go to what's called the global energy minima, I have to break a bond or break multiple bonds to get over that energy and then finally be able to fold. It's almost like if I told you, like, find the lowest, like if I said, like, if I gave you a plot, like a one mile each direction, and I just said, you're blindfolded, find the lowest point on this plot, and you just walk around and you find one low area, and it's like, oh, this is pretty low. I'm probably good. Well, that could be a local energy minimum, and you'd have to climb out of that hill, spend energy to get to the real global energy minimum. And I have a little demonstration on what that may look like for a protein. So I'm going to get out of my PowerPoint. And so you can see my lovely face again. Okay. Imagine this buttoned shirt, the way a correctly buttoned shirt is a protein that's folded in its native state. So if I put my shirt on correctly, this protein's now in the native state. So the unfolded conformation of my shirt protein is it like completely unbuttoned, thrown up on my floor, just like all wrinkled up. There are a lot of ways for my shirt not to be buttoned correctly, but only one way for it to be buttoned correctly. So that would be unfolded conformation, folded conformation. Now let's say when I was putting on my shirt this morning, I didn't have my coffee, right? And let's say that I like took this button, like that's down here, and I buttoned it up here on my collar. If I can do that without breaking my shirt. And then for some reason, I was super tired and I put my hand through here and I said, okay, I'm ready for work. This is a like intermediate conformation because all the buttons on the lower part of my shirt are buttoned correctly. However, there's a part of the protein, this button in my arm, that are not in its native state. To get out of this energy minimum, because this is not uncomfortable. I mean, you could wear a shirt like this. You have to put in energy to break this bond or to unbutton my shirt. I have to put in a lot of energy to do that while my hand's in here. Now I'm going to cheat and take my hand out. But you would have to put in a lot of energy or some energy to get out of that state. And that's what that hill's showing. And once you're out of that state, I can now button up my shirt correctly back to its native state. So in essence, you can think of a protein folding like putting up a buttoned shirt. Those hills are your intermediate conformations when it looks almost correctly, but you missed a button or you put a button in the wrong area. And you just have to put in energy to undo that button and re-put on your shirt. So any questions about folding funnel, how proteins fold, the energetics of folding, anything like that? So it's practically some of the protein is folded correctly and some of the protein is not folded correctly. So you must put in energy to break the parts that are incorrect and fix them. More or less, that's what's going on. Energy needs to be put in to get out of that local energy minima to go to the global energy minima. So it folded and it's not bad. You're making favorable connections, but it's not the best way you could fold. So is the hill in the energy minimum or is the bottom of the hill the energy minimum? The bottom of the hill is the energy minimum because negative energies are good. So the hills are saying this is positive energy because when you are getting out of this local energy minimum, you have to break interactions that were favorable. They're not the most favorable that protein can be in, but they're still favorable. So I have to break these favorable interactions so my protein can rearrange and go to the global energy minimum. Any other questions? Yeah, button-up shirt's actually a good analogy for a protein folding. What's the definition of a global energy minima? It's the lowest energy a folded protein can be in. Actually, it doesn't even have to do with protein. You can use global energy minima for anything where you're looking at free energy, and it's just the state that has the most negative energy out of your whole map or your whole area. A local energy minima is just, you look at one section of the map, or the funnel in this case, and you ask what's the lowest energy. Global is, I have the whole folding funnel, whole map in front of me. It's the lowest energy I can be in, the most negative energy I can be in. Again, whenever we talk about energy, negative energy is good, positive energy is bad. All right. So let's move on then. So during protein folding, some things might go wrong to have those intermediate conformations or local energy minima conformations. One of them is forming the wrong disulfide bonds. All right. So here we have our protein, which has 4 cysteines, cysteine 1, 2, 3, and 4. Now, in the native conformation, 1 and 4 are in a disulfide bond, 2 and 3 are in a disulfide bond. However, for the protein on the far left, 1 and 2 are connected and 3 and 4 are connected. That's bad. We don't want that. So there are specialized proteins that will help fix misfolded proteins. So this protein, I would say, is misfolded. Another term for that is non-native or misfolded, right? So this protein is called PDI, or protein disulfide isomerase. And what PDI does is that it will bind to a protein that has the wrong disulfide bonds. It will break those disulfide bonds and it will bind itself to the protein. Then, once the correct sulfur comes into contact, it will release the protein. So that's what the arrow is showing. Those of you who love organic chemistry and electron arrows, here they are again. So we have our electrons here to form our new disulfide bond. The way that this protein knows if a disulfide bond is incorrect is that if a protein is not folded correctly, you will have hydrophobic residues showing in water, right? Because proteins want to hide their hydrophobic residues. But if you're not folded correctly, you can have these hydrophobic residues being shown in water. That's super dangerous for a cell, because what can happen is that water will just start randomly pushing together hydrophobic residues from different proteins that are misfolded, and you get a larger and larger aggregation of proteins, which can eventually lead to cell death. PDI is one of those proteins that will bind on to the hydrophobic patch and then help rearrange disulfide bonds so they are correctly folded. And so a big picture question to go with PDI is, why would proteins have the wrong disulfide bonds in the first place? Because we said on, I think, Friday, primary structure dictates how a protein can fold. That's generally all you need for a protein. All you need is the primary structure, and a protein should fold correctly. So why do we even need PDI? Why do we have the wrong disulfide bonds forming to begin with? Proteins are not drunk, unfortunately. The protein dies, or the cell died, because of the aggregation protein. If you have a building up of hydrophobic groups in the cell and its aggregation, yes, the cell will eventually die due to toxicity. If you have stuff that is not soluble in the cell will die and won't be able to do its job. There was a previous question, so when we were talking about the energy funnel, how does it break those bonds? Like, how does it get out of that energy? A lot of times it's luck, where, there's enough movement in unfolded proteins, there's enough shaking that eventually they'll just break apart and find the correct pathway. So a lot of the times it's just like pure luck of, I'm kind of stable, but I'm not stable. So enough movement, enough energy is in me that I can just break those bonds and reform them. It's pure chance, no? they bind to close disulfide. Yeah, a lot of the times it is just like it's just random. I'm going to bind to the nearest thing I want to find. Keep in mind, right? Although I like to personalize proteins and like kind of think of them as people, because it makes it a lot easier to think about what they do in my own mind. Proteins are not smart, right? They have no intelligence. They don't know they're supposed to fold that in any particular way, especially cysteine. I'll get to why PDI knows how to fix it in a second. So if a cysteine is in close proximity with another cysteine, they'll just form a bond because that's chemistry. I'm an SH, you're an SH. You know what we do when we're together? We bond to form disulfide, okay? So how does PDI know that something's gone wrong if PDI itself is a protein and therefore not smart? This is how all proteins interact. They look for geometry and charge / hydrophobic profile. Put profile in quotes. So let's say there's a protein in your cell that like every time it's made, it will always form the wrong disulfide bond, like because it's coming out of the ribosome, right? And let's say when it's coming out of the ribosome, there's a cis here and a cis here. And since they're always close in proximity, these two cis's will form a disulfide bond, and you don't want that to happen. When they form a disulfide bond that's incorrect, some kind of intermediate state will be formed. And this intermediate state will probably look the same in every single copy of the cell because it's always misfolded the same, right? So this PDI, what will happen is in this misfolded conformation, you're going to have some hydrophobic groups pointing out into space, and they'll have some kind of geometry to go with them. So your PDI is basically just going around the cell, and it's like a magnet where if I find my match, which has the same, which is like hydrophobic and has the geometry I'm looking for, I'm going to bind onto it. And then when I bind onto it, I have been specialized enough to look for like a disulfide, and that should be close to me. And I'll break its bond and then reform another bond. So like PDIs have been evolved over millions of years to be able to just like bind onto a misfolded protein. It's been so specialized that it is looking for that exact misfolded, more or less motif, right? And once it binds that, it is so specialized that it has all the amino acids it needs arranged to break a disulfide and reform it correctly. Again, the protein doesn't know it's doing that. It is simply doing chemistry based on the geometry of all the amino acids, the geometry in both PDI and its target, and also because of charge and hydrophobic interactions. And every single protein, every single enzyme we talk about works the same way. It binds to its target because of geometry and its charge profile, and does chemistry based on its amino acids in the locations of other amino acids. And all of these interactions have been refined over hundreds of millions of years, if not billions of years. So they become very good at their jobs. So each PDI is specialized in a specific and wrong conformation until it reaches the right conformation, which shouldn't have a PDI. That's the way I think of it, yeah, right? Where this PDI is looking for an incorrect conformation and it fixes it. And once it fixes the wrong conformation to make the right conformation or native conformation, no PDI will recognize to bind that, right? No PDI has been evolved to bind it because imagine if you were like an organism that had a PI or PDI that finds a native conformation and makes it non-native. If that protein is important for you to live, you're going to die, right? Because you are taking a properly folded protein and making it improper. So if you had that protein, you're not going to pass that on to any generations because you're dead. And so that's why we generally don't see, a protein that will just go and misfold other proteins, because that cell's not going to live. So you can see, just by talking something as simple as this concept, we can tie it back to the bigger picture of protein evolution. And we're going to talk about it on Wednesday and Friday, this idea of protein-protein interactions and this idea of catalysts in terms of proteins. Any questions about the long diatribe I just went on? Does PDI guide the SH to the correct one? I have not looked at the mechanism of these PDIs in depth, but just knowing protein mechanisms in general, the way that this protein is probably set up is that, yeah, it will make sure that the correct cysteines come in contact so that they are forced to form a disulfide bond. That's usually how enzymes work. Because I'm thinking, what if there are more than two SHs close by? Again, that's something that would be probably worked out through natural selection, where if you do have multiple cysteines close by, the PDI has been like specialized enough to make sure the correct one is formed every single time, or like 99.9% of the time. When we get into enzymes, when we look at the active site of enzymes or the region of the protein that's doing the actual work, we will see that the mechanism is just so fine made. It's more or less so perfect that there's like hardly any chance for something bad to go wrong. It's just so packed in with amino acids that it does one thing, and it does it like perfectly. What would be the answer? Why would the wrong disulfide bonds form in the first place? Chance. Two cysteines are near and they will bind to each other because that's what cysteines do. Any other questions? And I'll just say for full clarity, I'm not so worried that you know why two cysteines would randomly form, but it's the whole discussion that question brings of this idea of why does PDI work? How does it know something's wrong? How does it make something right? So that whole concept is important to know in terms of biochemistry, and it has to do. And we're going to talk about it in depth in a couple days from now. But yeah, the actual answer is cysteines will just randomly form disulfide bonds with each other, and if they're just because they're close in proximity, that will happen. Can PDIs be mutated? Sure, everything can be mutated. It would be very hard pressed for any person in a lab to make a PDI to change a disulfide in a real protein. Humans aren't that smart. Computers aren't that good. We do not have the computational power to predict that. It would take way too long. Like by the time that I could predict that would probably be for like one PDI, it might be 10 to 20 years from now, right? Just working on that one thing using the computers we have now. Maybe not that long, but it would be so hard to do. But in theory, yeah, you could mutate it. Any other questions? All right. So what happens if a protein does not fold correctly, which will happen by chance, because when proteins fold and when proteins are in a cell, because of the temperature inside of a cell, there's a lot of thermal energy that leads to a lot of random movements. And what could happen is that proteins don't fold correctly. And as I stated earlier in this class, if proteins don't fold correctly, they could aggregate and form a big insoluble ball of protein, which will lead to cell death. Now, cells don't want to die generally, especially if you're a single cell organism, because that's the death of the whole organism. So cells come with these proteins called chaperones. And what a chaperone does is that it will bind to a unfolded protein, or a misfolded protein rather, and help it fold. So we're going to go through the process of one chaperone called GroEL, GroES. So GroEL and GroES are actually two proteins that work together. So GroEL is the chamber, GroES is its little hat. Now, for a functioning GroEL, GroES protein, you actually have two copies. So the green is one copy of GroEL. The pink is a second copy of GroEL, right? So these are two individual GroEL copies. Inside of GroEL, there's a chamber. However, you cannot go from one protein to another, right? If you go in green this way, you cannot go to red because there's like a barrier here that's not really shown in the picture. All right, so we're going to start in the top left, and we're going to walk through how this works. So if we start in the top left, we have ATP bound to our GroEL. And we have a misfolded protein that will bind. Once we have a misfolded protein bind, our GroES will come and form a little cap, right? This cap helps to prevent our misfolded protein from leaving. What will also happen, though, is that when this cap binds, the 7 ATPs that were bound become ADPs. So we dephosphorylate 7 ATPs, and we use that energy to change the shape of our GroEL, the inside chamber of GroEL. And this takes roughly 10 seconds, this whole changing of the shape. And when that happens, our protein inside GroEL will start to fold. And after that, what happens once we have burned our ATPs, a second different misfolded protein will bind our other chamber. 7 ATPs will bind. And once our second chamber has a misfolded protein and ATP bound to it, what will happen is that our GroES will pop off, our ADPs will pop off, and our folded protein, or better folded protein, will leave. Now, this protein might not actually be folded 100%, so it is possible that it will be rebound by another chaperone and try to be refolded. But that's the general process of what's going on. So I'll just say it really quickly again. So you have misfolded protein bound, 7 ATPs. When that happens, GroES binds. Once GroES binds, you take your ATPs and make into ADPs, and your protein will fold. A new unfolded protein will bind in the second chamber along with 7 ATPs. Once that happens, your GroES will pop off, your ADPs will pop off, and your better folded proteins will pop off. All right. So thinking about how GroES, GroEL works. Let's start in the very first step, right? Now, before my GroES binds, I want to bind a misfolded protein. Therefore, before GroES binds, what type of residues are in my GroEL chamber? And by type, I mean, what type of amino acids are pointing on the inside of my chamber or towards the face of the chamber? How does it recognize the misfolded protein? Hydrophobic region exposed again? Exactly. That's how I'm going to bind the misfolded protein. I'm going to bind to its hydrophobic regions. So if I bind to its hydrophobic regions, what type of amino acids must I have on the inside of GroEL to bind to it? Misfolded protein does not move through any barrier. What's happening from this last picture to this new picture is that they're just flipping the image to continue. So yes, a misfolded protein has hydrophobic groups exposed. If I'm a chaperone and I want to bind hydrophobic amino acids, what type of amino acids should I present to bind that? And they're not polar. What binds hydrophobic groups? If they're not polar and hydrophilic, they must be nonpolar. Charge? No. Remember, a misfolded protein has hydrophobic groups exposed. Water pushes hydrophobic groups together. That's the hydrophobic effect. If my role inside the cell is to help bind and fold misfolded proteins, you better have hydrophobic amino acids in the chamber to bind this misfolded protein. Okay, second part of that question then. So the first part, the answer is hydrophobic. Second part, my GroES binds. I'm using energy via ATP. And what's actually happening is that ATP is causing the inner chamber to rearrange, right? You're going through what's called a conformational change. You do a conformational change. All right. During that conformational change, you probably don't want hydrophobic amino acids anymore because you're trying to fold a protein. What type of amino acids are you going to be showing to your misfolded protein to get it to fold properly? The outside of the protein is not hydrophobic. The outside of GroEL is hydrophilic. Because if this part wasn't, sorry, the arrow's supposed to point there. If the outside was hydrophobic, that protein wouldn't go inside the cell. But the second part, during my conformational change, after I use that ATP, that energy, what type of amino acids are now inside my chamber or pointing towards the protein? Yeah, now you're polar hydrophilic amino acids, because think of the logic here, right? And it's actually very beautiful logic when you think about it. My goal as a chaperone is to bind misfolded proteins and fold them. So to initially bind them, I'm going to have hydrophobic amino acids pointing inside my chamber. So water will help with the hydrophobic effect and push these together. right? Now I have something bound. And I'm going to put on my GroES cap so they can't escape. I want to help them fold. I want to help them be inside the cell and be fully functional. So to mimic the contents of the cell, which is full of water, I'm going to hide my hydrophobic amino acids from them. And I'm going to show them hydrophilic amino acids, because those hydrophilic amino acids are kind of mimicking the effects of water, in that my protein will want to interact with these hydrophilic amino acids. They will want to hide their hydrophobic amino acids. What's the best way to hide a hydrophobic amino acid? Well, through a hydrophobic core. Right? So that's generally how that works. That's why we're using ATPs. We use that ATPs to more or less switch out what amino acids we're showing. At first, we're showing hydrophobic amino acids. Then at second, we are showing hydrophilic. So that's the answer. So at first, hydrophobic, and then hydrophilic. Questions about that concept? What causes the protein to go GroEL in the first place? That's the hydrophobic effect, right? Water does not want to interact with hydrophobic amino acids. And if I'm a misfolded protein, that means I will probably have hydrophobic amino acids showing to water. Water will make these hydrophobic groups aggregate. Well, if I'm GroEL, I have a ton of hydrophobic amino acids. So water is just going to push my misfolded protein into there. So again, we're using the idea of, I'm going to use the word again, that's not the best word, but like charge profile. In this case, my target is hydrophobic, so I'm going to use hydrophobic to lure it in. But yeah, it's again, kind of chance, but it's the hydrophobic effect. Water doesn't want to interact with our proteins if they're misfolded. Any other questions? All right, our second part. Oh, we do have a question. So it goes in GroEL because there's probably some water in there inside the inner chamber just due to chance, but water doesn't want to be there, and water is going to try to put another hydrophobic group in there instead. Yeah, chaperones, one of the big goals of chaperones is to fix misfolded proteins. That's their whole role. That's actually pretty much all that chaperones do. They help to fold proteins correctly. And not all proteins need chaperones. Most proteins just fold all right by themselves. Only some proteins need chaperones. So let's go to our next part then. So chaperones, another way to call chaperones, are heat shock proteins. In fact, the genes for GroEL and GroES are called HSP for heat shock proteins. So what heat shock proteins are is that they are turned on and created when a cell is under stress. The stress being usually heat. So heat shock protein. So I'm shocked by heat, I'm going to make these proteins. One of the things heat shock proteins do is that they will destroy proteins instead of refolding them like chaperones. So why do some proteins destroy? Why do some heat shock proteins destroy proteins instead of attempting to refold them? They just say, screw it, chop it up. Why? Who can think of a reason why? Is it an energy waster for energy? So when heat shock proteins are released, you are in like critical conditions. The sirens are going off. The ship is going down. You need to do whatever you want to save it. So you don't really care about energy at that point. You are going to die. So saving, it does take some energy to fold a protein. It also takes energy to chop up a protein. It probably takes more energy to chop up a protein, to be honest. Does it have to do with the cell being overwhelmed with the amount of misfolded protein? Too much energy investment. Again, it's not really energy, but it does have to do with being overwhelmed with the amount of misfolded proteins. They're like, we don't need to make this stuff. We have to focus on only the absolute necessities. That's kind of along it. Establish a protein conformation. So most chaperones do want protein conformations. I'm saying these don't. Okay. What happens, and I've said this a couple times in this class, what happens if you have a large amount of misfolded proteins? What is water going to do to those misfolded proteins? Put them all together, aggregate. What happens if you have a large protein aggregation inside of a cell? You die. Yes. So the idea of these proteins, we said at the very beginning when I was talking about the folding funnel. See, this whole lecture ties around. It all combines. Proteins are barely stable. They are less stable than the energy of 1 ATP. So if a cell heats up even a little bit, and we know this, right? Our natural body temperature is what, 98.7 degrees Fahrenheit. If you get to like 102, which is only 5 degrees, you are in serious trouble. Just 5 degrees, and your proteins inside your body are unfolding. You are in bad shape. You need to get that fever down now. So heat shock proteins are turned on when you get too hot because your proteins are starting to unfold very fast. If left unchecked, these proteins would aggregate naturally, and you could not clear them once they start aggregating. It's like Alzheimer's we talked about on Friday, and we're going to talk about on Wednesday. This plaque is going to form that you cannot do anything about. The cell functions will be inhibited by this plaque. This plaque will start interacting with other things like organelles, ribosomes, DNA. If you're a prokaryote, you die. You can't do your functions. So I do not want this aggregation to happen. Folding proteins take a long time, especially if you're in heat shock condition. Time is of the essence. So it's way faster if I just chop up my proteins, so they can't really aggregate. I'm just left with amino acids. So that's like my last ditch resort. I'm about to die. I'm gonna give myself some time in case I can get out of this heat. So for us, that means until your fever breaks. For an E. coli, that might be till moving towards a cooler spot. But yeah, that's the answer. Protein aggregation leads to protein death. One way to prevent that is to chop up proteins before they can aggregate. And it happens in heat because proteins are barely stable, and so they unfold even with the slightest increase of heat, which is why high fevers are super bad for you. This happens to literally all your cells in the body. So more or less when you have a fever, keep in mind when we study this stuff and when I talk about it, most of it is E. coli. So like GroEL, GroES, heat shock proteins are studied a lot in E. coli, but the same idea applies to eukaryotic cells as well. I mean, you get a fever, doctors are going to bring it down because your proteins are unfolding. And if your proteins are unfolding, you're dying. Your neurons are dying. Your cells are dying. Yeah, it's a very bad time. And that's also why it's a great defense, right? When you get sick, your body is trying to kill the invaders. How do you kill them? Let's turn up the heat and make their proteins unfold. I mean, that also kills you, but it will do a good job of killing them as well. All right, any questions? If not, I am over my time. So as always, I will put a homework up. We just have Alzheimer's to talk about very quickly on Wednesday. We already covered that on Friday. So I probably won't talk about it that in depth. Probably take less than 10 minutes. Other than that, we will move on to Wednesday's material on Wednesday. But yeah, that's all I have for you. So I will put this video up as always and see some of you Tuesday. See the rest of you on Wednesday. Take care.